Hey there, network orchestrators. Ready to dive into network operations? Today we're exploring how to keep the digital wheels turning, because someone has to keep the cyber circus running. If you think this sounds as riveting as watching bandwidth graphs, stick around. You're about to learn why network ops is like being a traffic controller for the internet superhighway. Except some of the cars are invisible, and sometimes they drive on the ceiling. In this video, we'll be discussing the essential aspects of how networks are documented, maintained, protected, and recovered in the event of failures. These concepts go beyond just theory. They represent the daily responsibilities and challenges faced by IT professionals who manage networks across businesses, schools, hospitals, and all types of organizations. Our goal for this video is for you to come away with a solid understanding of how proper documentation saves time and prevents disasters, the steps businesses take to prepare for emergencies, and the various tools that professionals leverage to keep networks running optimally and securely. So let's dive right in and start with the foundational element of successful network operations: documentation. Network documentation is vital for efficient operation, troubleshooting, and long-term maintenance of any network infrastructure. Just like you wouldn't want to assemble furniture without instructions, or cook a complex recipe from memory, you don't want to manage a network without detailed, organized records of its structure, configurations, processes, and changes. To illustrate the importance of network documentation, consider this real-world scenario. Imagine you're the new IT hire at a local accounting firm right in the middle of tax season. Suddenly, the network goes down. Clients are calling, accountants can't access critical tax software, and all eyes turn to you for a solution. With detailed documentation from the previous IT staff, you could likely identify and resolve the issue in a matter of minutes. Without it, you might spend hours troubleshooting while the business bleeds thousands in lost productivity. Network documentation serves many key purposes. When it comes to troubleshooting and problem resolution, detailed records allow you to quickly pinpoint and resolve issues by providing clear insights into the network's configuration and history of changes. This can dramatically reduce downtime and ensure more effective problem resolution. For network planning and scaling, accurate and current documentation is equally crucial. It helps network planners understand the network's present capabilities and limitations, which is essential for making informed decisions about expansion and upgrades. It's like having a clear blueprint of your current network infrastructure before planning any renovations. From a compliance and security standpoint, many industries have strict legal requirements that necessitate keeping detailed records of the network. Healthcare providers must adhere to HIPAA regulations, financial institutions, standards like SOX, and government contractors have their own set of security mandates. Documentation proves compliance and aids in security auditing. Change management is another area where documentation is indispensable. By carefully documenting any modifications made to the network, organizations can better understand the impact of these changes over time. This is required for maintaining network stability and planning future changes in a way that minimizes disruption. Finally, for knowledge transfer and onboarding of new team members, network documentation is a must. It enables new staff to quickly get up to speed on the network setup and history, rather than having to figure out everything from scratch. It also ensures that institutional knowledge doesn't walk out the door when staff turnovers occur. So, what should effective network documentation include? Network diagrams are a primary component. These visual representations encompass topology maps showing the interconnection between devices, detailing wiring schematics, and both physical and logical layouts of the network infrastructure. They provide an understanding of the network structure. Hardware and software inventories are another critical element. These are records of every piece of equipment and software on the network, including model numbers, licenses, software versions, and configurations. Such inventories are essential for asset management, upgrade planning, and responding to security vulnerabilities or equipment failures. Configuration files and settings for network devices must also be backed up. Having backups enables quick restoration of network operations in case of device failure or misconfiguration, drastically reducing downtime. Documentation should also include policy and procedure manuals detailing the standards and protocols for network operations. These documents are vital for maintaining operational consistency and are especially valuable for training new staff. Finally, proper documentation means keeping logs and historical records. Maintaining logs of past performance, changes, and issues provides data for analyzing trends, investigating problems, and improving the network over time. Equally important to what you document is how you manage and maintain that documentation. Consistency is key. Using standardized formats and having clear processes for updating ensures that anyone can navigate and trust the documentation. Accessibility is also important. Documentation should be easily available to those who need it, but it must also be secure, as it can contain sensitive information. Balancing accessibility and security is an ongoing challenge in network documentation. Regular updates are a must. Documentation must be reviewed and updated with any network change to maintain its reliability as a resource. There must be a clear process in place to make sure this happens consistently. While documentation should be comprehensive, it's important to be mindful of the level of detail. Recording essential specifics is vital, but getting bogged down in unnecessary minutiae can make documentation difficult to use and maintain. Striking the right balance is key. Finally, automated tools can be a significant asset in network documentation. Specialized software can help maintain real-time network maps, track changes, and streamline update processes. Leveraging these tools can greatly enhance accuracy and efficiency. In essence, network documentation is not just about record keeping. It is a fundamental practice for the operational health and stability of your network. It provides the foundation for informed decision-making, issue resolution, compliance, and continuity. Next, we have the tools of the trade, the symbols and diagrams used to visually represent the complex world of network infrastructure. Network diagrams are the visual language of the network infrastructure, and like any language, they have their own vocabulary, a set of standardized symbols used to represent the various components, connections, and functions of a network. Using these universally recognized symbols ensures that network diagrams can be easily understood by anyone with a basic knowledge of networking. So, what do these symbols look like and what do they represent? Let's start with one of the most fundamental components, the router. Routers are typically depicted as a rectangular box with an arrowhead pointing downward on one side to indicate its role in directing traffic between networks. The switch is typically represented by a long rectangle with a series of square buttons along one side, signifying the ports the devices plug into. In the world of wireless networking, the wireless router, or access point, is denoted by a symbol that looks similar to a wired router, but with the addition of waves radiating from the top. These waves represent the wireless signal the device broadcasts. Firewalls are often portrayed as a literal wall with flames or a checkered wall, indicating their role as a barrier against unauthorized access and attacks. Servers are usually represented by a rectangular tower with a series of smaller rectangles stacked on its side, signifying a server rack. Client computers, whether desktops or laptops, have their own distinct symbols resembling the devices themselves. The Internet, or really any network or cloud service, is frequently represented by a puffy cloud shape. Modems, the devices that convert signals between networks, are often shown as small rectangular boxes with a pair of wavy lines on one side, denoting the modulation and demodulation of signals. The connection between all of these devices are just as important as the devices themselves. Wired connections are typically represented by simple straight lines, often with a dot at each end to signify a plug. Fiber optic connections, which use light to transmit data, are distinguished by a series of alternating loops along the line, resembling a light wave. In the age of virtualization, it's not uncommon to see these symbols for virtualized devices. They can be denoted by a dashed outline or a special V symbol to differentiate them from their physical counterparts. But the symbols are just half the story. How they're arranged in a diagram is equally important. Diagrams should strive for clarity and avoid clutter. Labels and descriptions provide additional context, especially when documenting specific device models or configurations. The spatial arrangement of symbols, the topology of the diagram, provides a quick, intuitive sense of not just what devices are present, but how they're interconnected. A well-structured diagram can immediately convey key information about the network's design and function. Standardized symbols are crucial for effective communication in network design, troubleshooting, and documentation. They form a common language that allows network professionals to quickly understand and collaborate on even the most complex network infrastructures. While network diagrams come in many flavors, they can generally be categorized into two main types: physical and logical diagrams. Each serves a distinct purpose and provides a different lens through which to understand the network. Physical network diagrams are like a map of the network's physical geography. They show the actual tangible components of the network and how they're physically connected. This includes the exact placement of devices like routers, switches, and servers, the physical paths of Ethernet and fiber optic cables, and the layout of equipment racks and network closets. The primary purpose of a physical diagram is to document the physical reality of the network. It is an invaluable tool for planning and executing installation and maintenance tasks. When a network technician needs to trace a faulty cable or install a new server, the physical diagram is their guide. Imagine a scenario where a construction crew accidentally severs a fiber optic line. The network admin can refer to the physical diagram to quickly locate the exact point of the break and devise a plan to reroute traffic while repairs are being made. While physical diagrams deal with the tangible, logical diagrams are more concerned with the conceptual. A logical network diagram illustrates how data flows through the network, regardless of the physical layout. It shows the network's architecture in terms of subnets, VLANs, routing protocols, and firewall zones. Logical diagrams are used for understanding and managing the network's operation. They're invaluable for troubleshooting connectivity issues, planning network segmentation, and assessing security. For instance, a logical diagram would clearly illustrate how a company's public-facing web servers are separated from their internal database servers, even if those devices are physically adjacent in the same server rack. Consider a scenario where an organization needs to demonstrate PCI compliance for processing credit card transactions. The logical diagram would be key in showing auditors how cardholder data is segregated and secured as it moves through the network. Most organizations need both types of diagrams to fully document their network. Physical diagrams are essential for day-to-day operations and maintenance, while logical diagrams are for strategic planning and management. Together, they provide a comprehensive view of the network. They cater to different audiences and needs. The cabling contractor needs the physical diagram to know where to run the wires, while the security auditor needs the logical diagram to understand data flow and access controls. In the next section, we'll shift our focus from documenting the network to protecting it. We'll explore the strategies and technologies used to ensure networks can withstand and recover from disruptions, business continuity, and disaster recovery planning. In the realm of business continuity and disaster recovery, robust backup and recovery strategies are paramount. Imagine losing all of your critical business data, customer records, financial transactions, intellectual property, and having no way to recover it. It could be catastrophic. That's why organizations of all sizes must have well-defined processes for regularly backing up data and systems, and clear plans for recovering them in case of disaster. There are several distinct approaches to backing up data, each with its own advantages and trade-off. A full backup is the most comprehensive. It involves making a complete copy of all data every time the backup runs. While this provides the most complete protection, it is time-consuming and requires the most storage space. Incremental backups only back up data that has changed since the last full backup. This is faster and uses less storage, but can make the recovery process more complex, since restoring data requires retrieving the most recent full backup and then applying each subsequent incremental backup. A differential backup is kind of a middle ground. It backs up all of the data that has changed since the last full backup. This simplifies recovery compared to incremental backups, as you only need the last full backup and the latest differential. However, as time goes on, differential backups can grow quite large, as it continues to back up the same changed data until the next full backup. The frequency of backups is another consideration. Critical data and systems may need to be backed up daily or even hourly, while less important data might only need to be weekly or monthly. Organizations must balance the need for recent restore points with the time and resources required for more frequent backups. Where you store your backups is just as important as how you create them. Best practice is to follow the 3-2-1 rule. Keep at least 3 copies of your data on 2 different media types with 1 copy off-site. This could mean daily backups to a local server or NAS, with weekly copies to an off-site location or the cloud. Technology provides a range of solutions for implementing backup strategies. Traditional methods involve making copies to magnetic tape or disks and physically transporting media off-site for safekeeping. Many organizations are shifting to cloud-based backup solutions, which provide the benefit of off-site storage without the logistical overhead of managing physical media. Some are even moving towards disaster recovery as a service models, where a service provider manages the entire backup and recovery process. In the event of a disaster, the provider can quickly spin up replicas of the organization's critical systems in the cloud, allowing operations to continue with minimum interruption. Virtualization technology has revolutionized disaster recovery. By backing up virtual machine images rather than physical servers, organizations can quickly restore entire systems to different hardware or even to the cloud. But having backups is only half the battle. You must regularly test your ability to recover data and systems from those backups. Too many organizations learn the hard way that their backups were incomplete, out of date, or simply not functional when they try to use them in a crisis. This is where a well-designed testing strategy comes into play. This can include regular fire drills where you simulate a disaster and practice the recovery process. It can also involve testing to ensure you can meet your recovery time objectives, how quickly you need to get systems back online, and your recovery point objectives, how much data you can afford to lose. In essence, a robust backup and recovery strategy is about hoping for the best, but preparing for the worst. By combining the right backup methods, storage practices, and testing procedures, organizations can significantly mitigate the risk of data loss and ensure they can quickly bounce back from even the most catastrophic of events. While disaster recovery planning focuses on restoring data and systems after an incident, business continuity planning takes a more holistic view. It's about keeping the entire business running during and after a crisis. It involves proactive strategies to minimize disruptions and ensure that critical operations can continue, even in the face of major challenges. The BCP process starts with a thorough risk assessment and business impact analysis. This involves identifying all of the potential threats to the organization, from natural disasters to cyber attacks to supply chain disruptions, and analyzing the impact each could have on operations. The BIA helps prioritize which business functions are truly critical and what resources are needed to maintain them. Based on this analysis, the organization sets recovery time objectives and recovery point objectives for each critical function. The RTO defines how quickly that function must be restored after a disruption, while the RPO establishes the maximum tolerable period for which data might be lost. The next step is to develop strategies to meet those objectives. This might involve creating redundant systems, identifying alternate suppliers, or cross-training employees to fill critical roles. The specifics will vary widely based on the organization and its unique risks and requirements. All of these elements are then compiled into a formal BCP document. This plan details the steps the organization will take during an incident to maintain operations and communications. It outlines roles and responsibilities for the crisis response team and provides clear guidance for different scenarios. But a plan is only useful if it's feasible and up to date. That's why regular testing and exercising of the plan is crucial. Many organizations conduct tabletop exercises where key personnel walk through the plan step by step to identify gaps and improvements. Some even do full-scale simulations, enacting their BCP in a controlled environment to see how it holds up under realistic conditions. Employee training and awareness are also critical components of the BCP. Every member of the organization needs to understand their role in a crisis and be prepared to carry out the plan. Regular training sessions and drills help ensure that everyone knows what to do and can act quickly and effectively when an incident occurs. Communication is another key aspect of BCP. The plan must include clear strategies for how the organization will communicate with employees, customers, suppliers, and other stakeholders during a crisis. This might involve establishing dedicated hotlines, crafting pre-approved messaging, and identifying primary and backup communication channels. Finally, the BCP doesn't exist in a vacuum. It must integrate seamlessly with other organizational plans and processes, such as IT disaster recovery, emergency response, and operational continuity. All of these plans must work together to ensure a coordinated and effective response to any disruption. Business continuity planning is about anticipating the unexpected and being prepared to handle it. By systematically identifying risks, establishing recovery objectives, developing robust strategies, and continually testing and refining the plan, organizations can build the resilience to weather any storm and continue serving their customers and stakeholders no matter what challenges they face. While documentation and planning are essential, the day-to-day work of network operations involves consistent vigilance and proactive maintenance to keep systems running smoothly and securely. One of the tools in the ongoing effort is Simple Network Management Protocol. SNMP is a universal language that allows network devices to communicate their status and receive instructions. It works through SNMP agents installed on devices like routers, switches, servers, and printers. These agents collect information about the device's performance, capacity, and health and report it back to a central SNMP manager. This setup allows network administrators to monitor the entire network from a single pane of glass. They can track metrics like network traffic, device uptime, CPU, memory utilization, and a lot more. When issues arise, SNMP can alert administrators immediately, allowing them to respond before small problems become major outages. SNMP has evolved over the years to keep pace with the growing complexity and security demands of modern networks. The latest version, SNMP v3, adds security features like authentication and encryption to prevent unauthorized access and ensure integrity and confidentiality of SNMP communications. Another tool in the Network Admin's Toolkit is syslog. Syslog is a standard protocol used to capture log messages from network devices and systems. These logs contain detailed records of every event that occurs on the device, from routine operations to critical errors and security alerts. By centralizing these logs, administrators can gain a comprehensive view of activity across the network. They can use this data to troubleshoot issues, track changes, detect anomalies, and investigate security incidents. Syslog data is often a critical component for compliance reporting and auditing. For a higher level view, many organizations rely on network management systems. These platforms integrate data from SNMP, syslog, and other monitoring tools to provide a unified dashboard of network health and performance. But tools are only as effective as the processes and practices around them. Effective network monitoring requires diligence and discipline. Administrators must ensure monitoring covers all critical systems and that alerts are properly configured and promptly acted upon. They must regularly view and analyze monitoring data to identify trends and potential issues before they impact operations. Remote access is another aspect of network operations. Administrators need secure and reliable ways to manage systems and troubleshoot issues, often from outside the office. Secure Shell is a go-to tool for remote command line access. SSH creates an encrypted tunnel between the admin's device and the remote system, ensuring that all communication is private and secure. For complex remote management tasks, admins often turn to remote desktop protocol or virtual network computing tools. These allow them to take full control of a remote machine's desktop environment, which is helpful for tasks like software installations and complex troubleshooting. In some cases, physical access to devices is necessary. When remote access isn't possible or practical, administrators rely on console access. This involves directly connecting to a device using a physical console port in a terminal software. While this method is less convenient than remote access, it provides an important fallback for managing devices when the network is down or the device is otherwise inaccessible. Across all of these remote methods, security is paramount. Weak remote access controls are a common vector for cyber attacks and data breaches. Organizations must ensure all remote access is properly authenticated and logged, and that access permissions are carefully controlled. Virtual private networks should be used to encrypt all remote traffic, and multi-factor authentication should be mandatory wherever possible. This brings us to the topic of VPNs. In the modern era of remote work and global operations, VPNs have become an essential tool for secure network access. VPNs create a secure encrypted tunnel across the public internet, allowing remote users to access the corporate network as if they were physically connected. There are two types of VPNs in common use: SSL VPNs and IPsec VPNs. SSL VPNs are often used for specific applications and work through a standard web browser. They're convenient for users but provide less comprehensive network access. IPsec VPNs are the most robust and often used for site-to-site connections or full remote network access. They require specialized client software but offer greater security and control. Implementing a VPN involves several key steps. First, the organization must set up a VPN server to handle incoming connections. Next, users need to be set up with the necessary client software and login credentials. The network must also be configured to route VPN traffic appropriately and to apply the necessary security controls. Finally, security authentication methods must be put into place, such as digital certificates or multi-factor authentication. Regardless of the specific type and setup, VPN security is critical. Organizations must use strong encryption protocols and keep VPN software and devices up to date with the latest security patches. They should also implement access controls and regularly monitor VPN activity for unusual patterns or potential breaches. For network access control, two protocols stand out: Radius and TACACS. These protocols provide centralized authentication, authorization, and accounting services for network devices and resources. Radius, which stands for Remote Authentication Dial-In User Service, is the most widely used of the two. It is commonly used for managing VPN access, Wi-Fi authentication, and other types of network access. Radius combines authentication and authorization into a single process and encrypts only the password in the access request. TACACS, on the other hand, is more often used in enterprise environments for device administration. It separates out the authentication, authorization, and accounting function and encrypts the entire packet for added security. This makes it well suited for granular control over router and switch configurations and other administrative tasks. But Both protocols play a vital role in securing network access and ensuring that only authorized users and devices can connect. Organizations must choose the protocol that best fits their specific security and management needs and ensure that it is implemented correctly with strong encryption and robust access policies. In this video, we have explored the critical processes and tools that keep networks running smoothly and securely. We've seen how detailed documentation provides the foundation for effective network management, how business continuity and disaster recovery planning ensure organizations can withstand disruptions, and how ongoing monitoring and maintenance keep systems optimized and secure. These practices form the bedrock of modern network operations. Whether you're managing a small office network or a global enterprise infrastructure, mastering these concepts and tools is essential for your success. I encourage you to reflect on how these principles apply to your own organization or career aspirations. Consider how you might implement or improve documentation practices, disaster recovery strategies, or monitoring processes in your current role or a future position you aspire to. In the next video, we'll build on this foundation as we dive deeper into network security. We'll explore the ever-evolving threat landscape, the latest security technologies and best practices, and the critical role of security policies and compliance in protecting modern networks. Well done! You're now equipped to handle network operations like a pro, or at least you'll know when to panic appropriately. Stay vigilant and remember, in network operations, normal behavior is just a setting in your monitoring tool.